recording. Okay, in the second part, we're going to continue, but now we're, as I explained before, we're going to consider that the bars elements are not aligned. Okay, so what we have to do is we can establish a common reference system, so everybody will understand each other. So when he says X, that means that this direction doesn't mean this one. And then we can establish a continuity and also equilibrium. Okay, so that's next. Okay, let me see if I can share the screen. Okay, so here. This is 1.3. Okay, the example that I'm going, or the analysis that we're going to develop is in the plane, okay? Like in the 2D problem. In the general case, you will have to solve 3D problems, but the same procedure, you can imagine, that can be applied in that case. Okay, the only thing is that instead of one angle, that is the one that we need to check or define the relationship between these two reference systems. In that case, you will have to consider two angles in order to convert from one to the other reference system. But that's all. Okay, so let's go on. Let me use, I think this is black. Okay. So let's suppose that we want to analyze something like this. Okay, so we have joints here, here, and here. And of course, we have 1, 2, 3, 4 elements. Okay, so if we want to analyze this one here, we see that this is local X for the first element. Okay, but if you want to analyze this, which is connected in this joint, this is going to be the local X for the second element. Okay, so what do we do here? What we do is we establish a global reference system. For example, let's call it large Y, large X, large Y. Okay, so when we had to analyze bar elements which do not have the same local reference system. Okay, a common global reference system must be employed. Okay, so in this way, everybody will understand the same. And this will allow all elements to understand or have the same directions for its components. Okay. Remember that In this case, when we talk about directions, we talk about vectors, and we have two vectors here, forces and displacements. But the same treatment will be applied to both because both are vectors. So both will be transformed. Okay. I don't know what happened. This will allow all, I guess it says all elements.
Yes.
Okay. Okay. In this semester, we will consider elements in the plane, XY plane. But you can foresee the procedure for the general 3D case. Okay, so as I said before, the difference is that in this case, we consider only one angle to relate these two reference systems. In the general 3D case, you have to consider two angles. And of course, the algebra will be more complex, but that's all. Okay, so let's define two reference systems, okay? So we said X, Y with the hat, this is the local reference system for here, each element. And then we have X, Y, you see that there is no hat, this is the global system for the whole structure. Okay, so in this case, for example, as we said before, okay, this element, which is inclined, this is the local reference system of local X. For this horizontal, this is the local X. Okay, so and you can see something similar for this and for that. And we have a common, which is this one here. So what we have to do is to express the components of a vector in one reference system as function of the other. Okay, so let's see. Let's use black and white for the global. So this is the global. The no hat, this is the global. And now let's consider a second reference system, okay? And that's going to be, let's change color. Let's use blue. Here, this is the local reference system. This is X hat, and this is Y hat. Okay, now you see that this is the Z direction. So this is the positive rotation angle. Okay, so to specify the local, we say from the local, I'm sorry, from the global, we rotate an angle theta. So this is from the global to the local. Okay, and this is, you see that it is counterclockwise, and that's Z. So this is, in this case, is going to be plus about 40 degrees. Okay, so now let's do it. Let's consider one vector. Okay, one vector in the global reference system. So let's see this vector here. This is D, this is a vector. Okay, so, oh, Jesus. There. And immediately you can recognize that this is dx. So this value is dx. And again, this is going to be dy. In the blue, that's a local reference system, we can also specify the same vector, but the components is going to be different, are going to be different. So this is going to be dx in the local reference system, and this is going to be dy in the local reference system. Okay, so we can define different triangles, and I can leave you this as an assignment. You have to figure it out, but it's easy. It's just geometry. You can deduce the following: the dx local, that's from here to here, okay? You can have that as a combination of this value, see, from here to here, that's going to be dx cosine plus, and you need from here to here. That's going to be, see, from here to here is going to be this value, okay, that's dy times sine. So it's going to be dy sine of theta. Similarly, dy local is going to be equal to dy cosine of theta. I'm sorry, I forgot to put the angle here, minus dx sine of theta. Okay, this is just trigonometry and geometry. Okay, people, that's all. Okay, so we can write this in a more compact way in a matrix form. Okay. Oh, Jesus, let me. The computer is trying to save something, so let's be patient. Okay, so here we can write this thing in the following way. This vector so this is the dx local, dy local. And we can put it like the first line here, you see a cosine. So instead of writing the whole thing, I just write large C. And similarly for the sine, we have cosine here, it's multiplied by dx. So it's going to be minus sine here. And the other is multiplied by the dy is the cosine, like this. It's multiplied by dx dy. I suggest you keep this in your memory. So we are saying it's like in a compact way, we write like this. The vector in the local reference system is equal to a transformation matrix T, which is this one here, cosine sine minus sine cosine, multiplied by the components in the global reference system. Okay, so D local is equal to T times D global. What is T? Cosine sine minus sine cosine. Please repeat that in a couple of times and you will remember. Or if you have good memory, you just need to do it once. Oh, now, let's suppose that instead of, say, you take one vector here and you apply this transformation and you can express the components of this vector in the global reference system in the local one. In our case, in the case of bar elements, we have the displacement of two joints. Okay, so in the case of that, what we can do is we can simply put this in a very elegant way, as I will write it in a second after we get the, Jesus. Sorry. Okay. If we want to transform two vectors, okay, we can apply the following relation. Okay, so we go like this. So we said d1x, d1y. So these are the two components of the first vector in the local reference system. What we can do is simply, we can use this relation in here, and we can express that as function of the d1x, d1y. That's the global, the components of the same vector in the global reference system. And this is what we have. So we can split this like this, and we can take this matrix and put it into here. So it's going to be cosine, sine, minus sine, cosine. So we have transformed the first vector from the global to the local reference system. For the second one, the second vector, we said, okay, this is d2x in the local, d2y in the local. And again, it's the same transformation. So we take this and put it into here. So it's going to be cosine, sine, minus sine, cosine. And this is d2x, d2y. Now, this vector is completely transformed. So this part here, oh man, what happened with here?
Cosine.
It's cosine, thank you. So this is cosine. Now, what happened with this part? Well, that's the second vector has nothing to do with the first one. So we just fill it with zeros. Similarly for this one, the first vector has nothing to do with the second. So this is there. Remember, this is a transformation. This is not equilibrium or anything like that. It's just transformation. Okay? So in general, we can say, for example, that since we have two vectors, and we're going to apply this in the case of the bars, when we have two displacements, this can be summarized for the case of displacements and forces. As I said before, both are vectors. So we can say, for example, that d local is equal to, it's similar, but not exactly the same t as before, times d. Okay, so this thing here is here, which includes the two vectors. Similarly, that is this one here, includes the displacements of two joints, so are two vectors. But also, we can do the same transformation for the case of forces since they are vectors. So we can write the forces in the local reference systems can be transformed from the forces in the global reference systems. Okay? So this D vector has 4 elements. The first 2 corresponds to the 2 components of the first of the displacement of the first joint, and the second to these 2 components of the second joint, etc. And in this case, T is a 8 by 8 matrix, this thing here. Okay, it's a 4 by 4 matrix. See, originally for our bar, it was the relationship was just 2 by 2. Now we are getting close to a more real applications with this increased complexity of the problems. Now, before we apply this, we recall that our bars were elements which only applied in plane or longitudinal forces. But we are not going to change that. But we have to consider that the displacement in general could include vertical translations. So considering both components, we can rewrite the equilibrium of a bar element in the local reference system. Okay, so let me write to the left what we had before. So this is what we had before. We had F1 local, F2 local, and that was equal to EA over L. And then here we have 1, minus 1, minus 1, and 1. And that's multiplied by the displacement of both joints. Of course, we were considering only one single direction. Now, let me go back a little bit. And now you see that here on the left, we have this vector, which include, or this mathematical vector, which includes the displacement of 2 vectors, of the first and of the second joints. So what we have to do is we have to express this in a more general way. So we need to express this considering that have not only in the x direction, but also in the y direction. Similarly, for the second joint, we have d2x, which is this one here. But also in general, now we have to think that we have to consider the other component too. Now, on the left-hand side, similarly, we need this f1x, but now in general, we could have that. And similarly for the second joint. Now, we have EA over L, but the equilibrium cannot be changed. So we have 4 rows like this, and also 4 columns. Now, remember, this is a bar. That means that this term here implies strength only to longitudinal forces. Okay, so we should not have any force, any results in this equation. So what we can do is to keep this equilibrium and keep considering that they are bars. So these elements here along this row, the second and the fourth, they have to be filled with zeros, because this force here has to be zero in the local reference system. Let's wait a couple of seconds. Ah, here it is. So we have to have this, all of this equal to zero. Jesus. We have to have those zeros because there is no y forces, y component forces in the bar element. Now, this is what we have. So we have to recuperate that. So this one is multiplied by this one here. So this is what we have. And also, since we have a bar, this displacement here should not cause any force in the x direction, because this is a bar. So this also these spots has to be filled with zeros. So these two expressions are equivalent. So in the case of a bar, there is no local vertical forces at all. So if we include some terms, some components in the y direction multiplied by zero, the result doesn't change. So this is the same. Okay? So we can summarize this in the following way. So this is the external force of both joints, but in the local reference system. You see, this is a hat. Okay? And that's going to be equal to the K matrix local reference system multiplied by the displacement of the joints in the local reference systems. But now this K is equal to this K, okay, considering both components. We recognize that since we're working with bars, the vertical, this line here, should not participate, should not contribute to this, to the strength of the element. And we have to just fill it with zero. Now we're ready. This vector here is in the local reference system. This vector here is also in the local reference system. But we have obtained expressions to transform those vectors from the local to the global reference system. So this is what we're going to do. Let's replace F and D in the global reference system. So instead of this, we write T times F, no hat. That means that this is in the global reference system. On the right-hand side, this is equal to K. And also, this vector can be expressed as the product of the transformation matrix times D, but in the global reference system. So we can express something similarly to the equilibrium that we had before in the following way. So we can say that F, we take this and we put it to the right. Remember, if it is on the left, has moved to the left also. So this is going to be the inverse, times K, local, times T, and times D. This is very similar to this one. We have external forces, but now in the global reference system, it's equal to a matrix. It's a very long matrix, but a matrix after all, multiplied by the vector of the displacements, but also expressed in the global reference system. We say what we can do is simply combine this operation, and we can call it as the K. Remember, this is not, there is no hat. That means that it's in the global reference system. And we can express this simply we can say that F is equal to one of the properties that this transformation matrix has is that the inverse is equal to the transpose. So let me write it like this. So it's the transpose of the transformation matrix times K and times T, and it times the displacement vectors. Okay, so this is just the result of the property of the transformation matrix. Property of T. So this is going to be called K, little k, no hat. So this is the equilibrium for each element, people. Like that. Questions about this procedure? Questions about this procedure? Okay, so what we have to do now is now we can apply finite element method for system composed by bar elements in the plane. So for example, the simplest case, let's suppose that we have something like this. We have something like this and like that. So for the element 1, this is going to be the local reference system, right? This is going to be the Y local. For the second one, let me change color. For the second one, we could see that let's suppose that we want to set this as the second. And again, this is going to be the local in the Y direction. So for this case, for the second, this is going to be theta for the second element. Let me include here also to complete this figure. So we have for every element, black and I don't know what color is whatever. It's a orange. We have This is a local, and this is theta 1. With this theta 1, we can convert the displacement of this and this joint from the local reference system into a global reference system. Similarly, for the second, I'm missing, I did not include the global reference system. Let me use, is there, oh no, there's no. So here, we can say, for example, that I don't know, maybe if you want something like this is going to be X and Y. So X and Y is a global reference system. So what we have to do here is take the black element. Here we have theta, we have EA, and the length is from here to here, and transform using these relations, this equation, from the global to the, to the local, from the local to the global. And then we have to do something similar with the red one, the second element, and transform. And now we can say that the continuity, for example, in this common element, okay, can be expressed because this joint moves to the right a certain amount, and that direction is the global. And when we combine with the second element, again, this element, this joint for the red element is going to move to the right. So the two elements are talking the same language. Okay, that's what we are going to do next. Okay, so we can solve this. We can complete this product. Okay, T transpose K and T. This K with the hat, we have it up here. Okay, this is the K hat. The T, we had it before when we convert two vectors instead of one. Here, this is the T. So we could develop this procedure, T transpose K T. This is a long expression, but we could try to complete this deduction with this. So we can say developing
Doctor.
Yep.
One question. I have to put for each element local system reference.
Yes. And with that, what you have to do is, what does characterize a local reference system? How do you characterize a local reference? How to identify a local reference system?
The direction of the element.
Exactly. That's all. That's all. So first, you have to write what is your global reference system. In this case, I'm writing the local X to the right, but you can specify the local in the way you want. For example, you can take this direction as your local reference system. I'm sorry, as your global reference system. And in that case, the first element is aligned with the global reference system. In that case, theta 1 is going to be 0. But there are different ways. For example, in the case of the ship, what's the X direction for you, typically? In the direction of the length of the ship. You can specify any direction that you want. For example, you can say, okay, I'm going to take the global X direction pointing upward. Yeah, as long as you clearly define it, there is no problem. Okay? And then every element will be, the local reference system of every element will be specified with the position of its joints. So if I take this global reference system and I say this joint is a certain XY position, and similarly for this one, okay, I can calculate this one here. Inverse tangents of delta Y divided by delta X. We have to be careful with the sign of this arctangent, but that's all. That's all. Did I answer your concern?
Yes, doctor. Thank you.
Okay, no problem, no problem. Let me save just in case. Okay, so before we go to the break, let's write this in a, still saving. Still saving. Well, let's take a break here. Let's take a break here. And when we return, we will go on with the full expression. It's a full 4x4 matrix to express the stiffness in the plane of a bar. Okay, so let's take a break.